All right, so today we're going over more quadratics, graphing by hand. Our I can statement is exactly what you think it is. It's I can graph quadratic. If I could spell quadratic, that's fantastic. Quadratic equations by hand. I'm actually going to change equations to functions. I did start recording. I did. Okay. Oftentimes we can use this table of values to find the, what they call them in this, roots or solutions. If you remember from yesterday, they're also called the x-intercepts. Or zeros. You should be able to identify what it's asking for when you're being asked from any four of these. I'm going to rewrite that T. If you're asked to find the root solutions, intercepts, zeros, you should be able to know what they're looking for. So, when we're given a function, the easiest way to graph it is to make a table of values. So, that's what we're going to do first. We have minus 1, minus 2, minus 3, 2, 3. These are kind of chosen arbitrarily, mostly because they capture the vertex. So if we plug 0 in for x squared, we get 0. If we plug 1 in for x squared, we get 1. We get 4 out for 2, and 9 out for 3. Because it's a quadratic, we know it's symmetric around the vertex. I'll give it away. This one is our parent function. It is our simplest form of the function, of a quadratic function. When we graph it, it looks something, not something, it looks exactly like this. So we go 2 up 4, over 2 up 4, and 3 is off our charts. So if we draw our line of symmetry in, where it splits the function in half, we can see our line of symmetry is at x equals 0. If it will let me write x equals 0. Our vertex is at 0, 0. As we can see, because x is our first value, when we have 0 in for x, our output is y. The graph is pointing, or the function is pointing upward, so it is a minimum. We have the function touches the graph at one point, and if you remember, when it only touches at one point, it is our vertex is our only 0. Who could tell me the domain? All real numbers. That fancy R. Our range is y is greater than or equal to 0. It is pointing upwards. Our y component of our vertex is 0. I'm going to rewrite that because that looks like garbage. Y is less than or equal to 0. Moving on to our next example, a little more complicated. Oh, okay. I'm going to start filling out the table. Minus 2 and minus 3, 1. All right, 2 and 3. So then we're just going to plug these these values of x into our function. So if we plug 0 in, we'll get 0 squared plus 3 times 0 minus 2. We get just minus 2 out. I trust you all can use a calculator and put these in, so I'm just going to fill out the table for us. So we have minus 20, minus 12, minus 6, minus 2, and then 0, 0, and then minus 2 again. And when we graph this, so we have 0, minus 2, 1, 0, and 2, 0, and then 3 is minus 2 again. Minus 1 is at 6. So our graph is going to look something like this. So if we draw our line of symmetry, it's actually in between the points 1 and 2, where x equals 1 and 2. So our line of symmetry is that x equals 1.5. Which means our vertex is at 1.5. If we plug 1.5 into our equation, we'll find out that our vertex point is at 0.25. I plug it in. I'm just trying to save time by not having to do all the math on paper. And graph is pointing downwards, so we know this is a maximum. Can anybody tell me our x-intercepts? X-intercepts, zeros, roots, whatever you want to call them. They're in the table. Alrighty. So our x-intercepts are at 1, 0, 2, 0. Our domain, as we already know, is all real numbers for all parabolas, and our range will be y is less than or equal to 0.25. I don't know why I opened my downloads. Last but not least, so we have f of x equals x squared minus 9. You'll notice that it's just like our first function, but with minus 9 at the end. So all we have to do comparatively is just subtract 9 from all of our components in our first table. So first we'll write our x values. So in our first one, 0 was 0. So that means 0 is minus 9, and minus 8, minus 5, and 0. And 0. So when we graph this, our vertex is going to be off our page right now. Our zeros are at minus 3, 0 and positive 3, 0. At minus 2, we are at minus 5. Positive 2, we are at minus 5. We have our function. And just like our previous one, our equation of symmetry is that x equals 0. Looking at our table, we have 0 and minus 9. That means our vertex is at 0, minus 9. The function is pointing upwards, so it is a minimum. If it would stop scrolling on me. Minimum. Our zeros are given in the table as minus 3, 0, and positive 3, 0. Our domain, as we already know, is all real numbers. And our range is y is greater than or equal to minus 9. Alrighty. So, what if we don't want to graph it? Is there a way for us to find our axis of symmetry without it? Yes, it is. So, finding the axis of symmetry and vertex using, scary word I know, math. Don't ask me, I didn't make up these. Fill in the blanks. So, the formula for finding the axis of symmetry is negative b over, I don't know why I did that, over 2a. 2 times a. So if we remember our standard form for a quadratic function, it is, stop opening function, y equals ax squared plus bx plus c. These are the values you would plug in, so I'm going to make them capital to make them a little easier to tell the difference. So to find the axis of symmetry for these functions, so we have our a equals 2 and b equals 4. So we'll have negative 4 over 2 times a, which is 2 times 2. So x equals negative 1. Over here, same deal. A equals 2, B equals negative 6. So we'll have negative 6 over 2 times 2, which is negative 3 halves. Oh, sorry. We need to negate it, so it's negative b, so it's negative 6 or positive 6. So it is positive 3 halves. Or you could write it as a decimal as x equals 1.5. Either is fine with me. You can keep it as a fraction, you can keep it as a decimal, whatever works for you. Over here, our a is 3 and our b is 9. C is 2. We have negative 9 over 2 times 3 equals x. That equals random scrolling. Negative 9 over 6, or 1.3, or it's also 3 halves, negative. So when we do this, we are finding our x value. As I've already said multiple times before, when we find our axis of symmetry, we're actually finding the x value of our vertex. And because of giving us the x value, we can find the corresponding y value, which will help us find our final vertex. Oh, too much scroll. So with that, we're going to do a couple examples, find the axis of symmetry again, and then we're going to draw it. So I'm going to have you guys help me with this one. For number 1, what is our a value? A equals 4. What is b? B equals 8. So what is our axis of symmetry? Looking at our equation, we'll have x equals negative b over 2a. So if we plug in our values in, what do we get for x? So it's going to be negative 8 over 8. So we get x equals negative 1. And if we draw that, it's going to be a vertical line where x equals negative 1. So over here, what is our a for number 2? What is our b? Negative 12. So when we plug it into our function, we'll get x equals positive 12 over 2 times 3, which when we simplify that, we get x equals 2. And to draw it, it is a vertical line where x equals 2. So, how do we find the vertex using the axis of symmetry? Well, we plug in the x value into the function. So right off the bat, our a equals 4, b is, why did you keep randomly opening stuff, computer? So b equals 8. So using our equation, x equals negative 8 over 2 times 4. We get x equals negative 1 again. When we plug negative 1 into the equation, we'll get 4 times negative 1 squared plus 8 times negative 1 plus 5. So that's going to be 4 minus 8 plus 5. So y equals. That means y equals positive 1. Our vertex is at negative 1, positive 1. And I'm going to patience. Come on. There we go. I'm going to move this down here just to clean it up a little bit. So vertex is at negative 1, 1. So over here we have a equals 3, b equals negative 12. Might notice the exact same function from up above. So x equals 2. So when we plug it into our equation, we get y equals 3 times 2 squared minus 12 times 2 plus 9. 2 times 2 is 4. 4 times 3 is 12 minus 24 plus 9. Y ends up equaling 24. So that means our vertex is at 2, negative 3. So our final one, we're going to put some of this stuff together. Step 1, find your axis of symmetry. So for this, that's our x equals negative b over 2a. For this one, that's going to be negative 8 over 2 times 2. So that equals negative 2. So if we draw our axis of symmetry, it's going to be at negative 2. Step 2, find your vertex. By plugging it in. So y equals 2 times negative 2 squared plus 8 times minus 2 plus 5. Y equals 8 minus 16 plus 5. When we simplify this, negative 8 plus 5, we get y equals minus 3. So our vertex is at minus 2, minus 3. And then we can do the rest by making a table of values. So since we have our vertex, we can make sure that it is one of our values. I'm only going to ever require you guys to draw at least 5 points. So that's your vertex and 2 around it. So if we have our vertex is at minus 2, minus 3. So add 1 to each one, so we'll get minus 2, minus 1, 0, minus 3, and minus 4. And step 4 is just going to be graph. I don't know why there's so many extra lines for it, but it's just going to be graph our values. So if we plug in 0 into our equation, we get y equals 2 times 0, which is 0, plus 8 times 0, which is also 0, plus 5. So, nice and easy. When we plug in minus 1, we get y equals 2 times minus 1 squared, plus 8 times minus 1, plus 5. So that's going to give us 2 minus 8 plus 5. So y equals minus 1. And because our vertex is minus 2 minus 3, that means it is symmetric across the other side. So that means this is also minus 1, and that means that is also 5. So then we can plot it. And 0, 1, 2, 3, 4, 5. Moving over. So if you have 5 points, that is enough to graph the parabola enough to see how it is going to respond. And that's it. I'm going to scroll down. Turn off the